Okay, let's take a look at a second example, convolution example. Here we will convolve a unit step with a pulse. Make it, this particular pulse begins at t equal minus 2 and then ends at t equal to 2. And so in this case we can time reverse either one of these. I'll sketch what they both look like as a function of, I'll go ahead and make the variable change to tau. So x of tau is u of tau. Again, it just looks like this. It's 1 for all tau greater than 0. And then h of tau is going to look like this. It starts at tau equal to minus 2 and is 1 between tau equal minus 2 and plus 2. So it's just a rectangular pulse that looks like this. It goes to 2 here. Again, we want to time reverse the simpler of the two functions. It's maybe debatable which is simpler here, but I'm going to time reverse the input. So what that would look like, again, time reverse this, and then the origin is shifted to t. So I'm going to show it for the case here where t is less than minus 2 so that there's no overlap. So in that particular case, for t less than minus 2, there's no overlap between x of t minus tau. No non-zero overlap, so everywhere h of tau is non-zero, x of t minus tau is 0, as long as t is less than minus 2. So in this particular case, the integrand is 0, and y of t would be 0. Again, for all t less than minus 2. It doesn't matter what t is, as long as it's less than minus 2. Now let me try and draw the case where t is between minus 2 and 2. So in that case, x of t minus tau looks like this. Okay. And then in this particular case, we'll have a non-zero product only between minus 2 and t. I'm going to draw that, what the product looks like right over here to the side. For all tau less than minus 2, h of tau is 0. And then for all tau greater than t, x of t minus tau is 0. So this is non-zero. T can be anywhere in the region here between minus 2 and plus 2 in this case. So I'll just show t right here. In this region, both functions are equal to 1, so the product would also be equal to 1. So again, I'm sketching the integrand. This is actually what h of tau, x of t minus tau looks like for t between minus 2 and 2, and this is t here. In this particular case, so the limits on t are minus 2 less than t less than 2. In this particular case, I want to integrate this. I could formally integrate it, but it's just a rectangle of height 1 and width t minus a minus 2. So in that case, the area would be the height times the width. T minus a minus 2 would be t plus 2. And so the result is just t plus 2. And then the third case we have to consider, because the limits on our integrand are different, is the case when t is greater than plus 2. So again, this is what x of t minus tau looks like. So here's 2, here's t. Now in this particular case, what the product would look like is, again, h of tau is 0 for all tau less than minus 2, and it's also 0 for all tau greater than 2. So the product, again, here would be 0 for tau greater than 2. So when in the case where it doesn't matter what t is, as long as t is greater than 2, the form of the integral won't change. It'll look exactly like this. It'll have a height of 1 and a width of 4. So in this region, for t greater than 2, we have y of t is equal to 4. So let me go to the next slide here. I could write this in a couple different ways. I'll just write it like this. Y of t is equal to, I'll write it out in the 3 different segments. It's equal to 0 for t less than minus 2. It's actually equal to t plus 2 for t in the region between minus 2 and plus 2. And it's equal to 4 for all t greater than 2. So I can sketch what that looks like. This is y of t. It begins at minus 2. It's 0 for all t less than minus 2. So we're sketching the output as a function of 2. And then it's this straight line segment, t plus 2, in the interval between minus 2 and 2. At minus 2, t plus 2 is 0. And when t is equal to 2, this thing gets up to 4. So the straight line segment looks like that. Reach a height of 4. And then now for all t greater than 2, the output is a constant 4. Okay. Just a couple of notes on this. And this is a perfectly fine way to express that. I could write it in a different form. I can take the t plus 2 times this pulse that exists between minus 2 and plus 2, and then add in this segment for all t greater than 2. I can combine these terms to write it a little more simply as t plus 2 times u of t plus 2, and I'll combine this term with the u of t minus, the 2u of t minus 2 terms, and I get minus t minus 2 u of t minus 2 as, again, an alternate but a equivalent form for the output. Okay. Couple of other notes here. This particular case, if you recall, x of t was just a unit step. H of t actually looked like this. And recall, h of t represents the response to an impulse at t equal to 0. So in this particular case, the impulse response starts before the impulse arrives. So this is an example of a non-causal system. Okay. And again, in our particular case, with this as input, unit step as input, arriving at t equal to 0, we got output before the unit step arrived. Again, that can happen with a non-causal system. But remember from our convolution properties we know that the start of the output is going to be at the sum of the start times of the input and the impulse response. So the 0 plus the -2 is equal to -2, and our output actually starts at t equal -2. If I shifted h of t here to make it causal, if I shifted it 2 seconds to the right, our output would actually shift 2 seconds to the right, and then would correspond to, we'd have a causal system, and in that case the output would not start until t is equal to 0. Alternatively, I could look at x of t as being my impulse response. And then in this case, this is a causal function, so it would be a causal system, and then I could treat h of t as the input. In that case, h of t actually starts at -2, and then I would expect my output to start at -2, which it does, and we get exactly the same result if I convolved x of t with h of t as when I convolve h of t with x of t. I guess the final thing to note is that the output is continuous. There's no E there. Is continuous. So by that I mean the output between these different segments, notice that for t less than -2, the output was 0. It was also 0 exactly at t equal to -2. And then as I transitioned to t equal to 4, I'm just showing an arbitrary continuous function here. When I get to t equal to 2, my line segment got up to 4, and then the function was 4 forever after that point. What I mean by continuous is that I mean that there are no jumps in the function. I don't have an instantaneous jump here and then another instantaneous jump as I go between these different segments, between at -2 and 2, for example. So that's a nice check. Our convolution will always obey that as long as neither the input nor the impulse response contain an impulse. Okay, if either one of these involves an impulse function, then we can get a jump in the output. But if neither of them involves an impulse, as long as they're unit steps or unit ramps or exponentials or actually anything other than an impulse, the integration, the convolution integral, that integration smooths out any discontinuities, and so I won't see any jumps in my output. So knowing that allows me to do a quick check to see if my convolution result is correct.